Okay, class, welcome to 3.1. So before we dive into 3.1, where we begin matrix algebra, I just wanted to highlight a few things to make connections with the algebra of real numbers that you already know. So some of the advantages of algebra is it allows us to represent relationships between quantities, like writing formulas, so we can easily see how things are related and how you can compute one thing if you know other things. You can set up and solve equations. It's one of the most powerful things we can do with algebra. So it gives us a set of tools to find an unknown or some unknowns given information about other things. We do that by solving equations. It also allows us to express and find equivalent expressions. Sometimes some expressions are a lot easier to use or to think about or to make sense of or to compute with than others. So these are some basic advantages. There is a big disadvantage. The notation hides meaning, so it takes time and effort to learn and use effectively. Right, so the variables and the rules that you use associated with them on how they work. The algebra of real numbers has the real number rules, but those aren't tied to the notation that you use itself. They're hidden. When we dive into matrix algebra, it's going to allow us to be very compact and have one symbol represent a whole bunch of symbols or a very large matrix. That's going to save us a lot of writing and time. So that's one big advantage. But one disadvantage is it seems to hide more than the algebra with real numbers. The rules of matrices are even more. There are even more restrictions. For example, most of the time they don't commute with multiplication, so you have to be really careful about what you're doing. You have to understand the rules as you use it. So a bigger advantage and a big disadvantage. So let's dive into the slides. I think that's the first real one, yeah. So we call an array of numbers a matrix. It's a rectangular array. We call the number of rows, we usually refer that to m, and the number of columns as n. And each of the elements or entries we can assign it a location or a name by the number that they have. Aij is really AMN, or that didn't turn out very good. I is which of the m rows, and j is which of the n columns. So you can see that. So this is a lot of vocabulary in this one, and notation. So we can write a matrix if we have representations of the columns. We can just write the matrix this way, where A1, A2, etc. are column vectors. And similar with row vectors, if each of these is a row vector, then you can write the matrix that way. We've already been going back and forth, especially with thinking of columns as vectors, column vectors and matrices when we talk about augmented matrices and looking for linearly dependent and independent variable vectors. If you only have entries down the diagonal, if these entries are the only ones that might not be zero, it's called a diagonal matrix. Okay, some of them still could be zero. If all the entries are zero, it's just called the zero matrix. Diagonal matrices turn out to be really nice. We'll bump into those, especially late in the semester. This is a very special matrix called the identity matrix. It just has ones down the diagonal and zeros everywhere else. And the reason it's called the identity is because if you take an identity matrix and you multiply it by any other vector, then you just get that same vector. So So it works the same way as the number. Has the same multiplicative property as the number 1 with the real numbers. So, and these are special column vectors. These are called standard unit vectors or the standard basis vectors, or sometimes elementary. These are the elementary column vectors. That's why they use E here, where you just have 1 and then all the rest is zeros. 0, 1, and then all the rest zeros. These correspond to the vector of like just in the unit vector in the x direction, a unit vector in the y direction, a unit vector for the z direction, etc. So adding matrices, you add matrices just by adding up their components. So A1 and B1. If you're adding A and B, you just add up each of the components. So the new entry in that place is just A1 plus B1. So 1, 2, 3, 4 plus 1, 1, 1, 2 would be 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 2 is 6. So you just add them that way. This makes sense if you think about foods. If you're combining foods, or using some foods to make new foods, then like you'd add the corresponding entry that might correspond to, like, this row might be fat, right? So the fat of food would correspond to the fat of the other food, etc. Okay, not the best. I obviously didn't prepare on that explanation. So that's adding. One thing to emphasize here, you have to have the same size matrices to add the matrices. Matrix multiplication, this is the one that throws everyone for a loop. But one of the main reasons I wrote the peanut butter book was to have matrix multiplication make sense. There's a whole section on it. If you don't remember it, please go back and read it. One of the key ideas for me in helping it make sense is I've been writing things like this: x times 1, 2 plus y times 3, 4. We've already been writing things like this to represent different combinations of column vectors. Like how much of x, if I have x multiples of the 1, 2 vector and y multiples of the 3, 4 vector. Sometimes I want that to equal a certain thing, right? And then I'm solving for x and y. Well, here, I'll even put this down, 0 and minus 5. Like what values of x and y would make this true? Well, we can rewrite all of this as, like, the only thing that isn't a packet here are this x and y. And we can rewrite all of that if we combine 1, 2, and 3, 4 into a single matrix, and we combine x, y into a packet of unknowns. Then we get this. And this is the notation. These two things are equivalent, the left-hand side and the right-hand side here. And so this gives us a rule for how to multiply a matrix times a vector. So the x gets multiplied by all of the values in the first column, right? That first vector. The y gets multiplied by all the values in the second vector. Then you add them together. So that is the same as x plus 3y and 2x plus 4y equals that same thing. So this and that, they're the same expression. And when it comes to doing a matrix times a matrix, you just take each column at a time to produce the next column. So So if you ignore all this for a minute and you just focus on this vector here, the matrix times this vector, we can think of it as 2 times 1, a minus 2, 1, plus 0 times a minus 1, 1, 0, plus 3, 2, 0, a minus 2, plus 1, 1, 1, 3. And that's a straightforward computation. 2 times all those entries, 0 times all those entries, 3 times all those entries, 1 times all those entries, and you add them up, and you're going to get a vector, and that vector is the first column of your new matrix. And then you move to the second one. And so you get this one times those. So you have a minus 1 times 1, a minus 2, 1, plus 4, a minus 1, 1, 0, plus 1, 2, 0, minus 2, etc., plus 2, 1, 1, 3, equals, and then you can do that computation, and it goes right there. So in practice, what students usually do, they don't usually write out all these, but this is the place, this is one way to understand why we end up multiplying matrices and vectors the way that we do. In practice, students usually think in their minds 2 times that, 0 times that, 3 times that, and 1 times that, and then they add those up. So that's a 2 plus a 0 plus a 6 plus a 1, and then that all comes right here. One thing to notice that this is, every one of these entries, each entry is a dot product. So the dot product of this, let me change colors. The dot product of this row and this column is this entry 9. So it is a dot products are emerging again. It's another bunch of dot products. Okay. And vectors, they don't have to be the same. Matrices don't have to be the same size to be multiplied, but this number here, this n here, has to be the same as the m on this one. So if this is m by n and this is m by n, well, m1, n1, m2, n2, then these have to be the same, because you have to be able to do the dot product. So this would have this column has to have 4 entries to match up with the 4 entries in that row. And there's some examples they do right there. Notice BC and CA can't be computed. B times C, this and this don't have the right number. They don't have the same length, so you can't do that dot product. So, or you could start writing 5, this 5, times 5, 2, 1, plus this 3 times this column, 3 minus 1. Gosh, it sure doesn't like these, like 3s. So it tries to change them up. Plus, and then you get this 1, but you don't have another vector over here. So you don't have another column over there to put in there. So it doesn't make sense to multiply those. Okay. Another key thing to notice here is that matrix multiplication, if you take two matrices, A times B is not the same as B times A in general. There might be some special cases where there are, of course, but in general, they're not the same. Here, you can do AC, but CA isn't even defined. And this is something I just used earlier. We can rewrite systems of equations as a product of a matrix times a vector, and where that vector is an unknown. And this is really nice, because then we can start writing vectors like this, or write systems of equations like that, and we can start writing larger equations and start solving things. We've been really close to writing that several times as we've done systems of equations, but we haven't written it down exactly. So here we have the column of unknowns. That means 2, 7 plus x2, 1 minus 2 plus x3, 4, 4 equals 10, 9. So that is one way to represent what that product means. Of course, you can also represent it this way. This way highlights the combinations of vectors. How much of each one do you get? So, and there's the augmented matrix. Go ahead and read that. If we treat each column of B as a matrix itself, we can rewrite AB as A times like this column, this column, this column. This emphasizes that each column, I tried to emphasize this before, the first column of the product is really just the matrix times the first column over here, and then you get a new column you can write down there. So you can simplify all of the matrix times a matrix products into just a matrix times a vector, and then another matrix times a vector, and another matrix times a vector. And those are your those new products. Those products are your columns. Similarly, there's a way to do that with rows. Sometimes, I probably will have done an example, a real-life example of this already by the time you watched this in class, where sometimes we want to think about a matrix as like this. We might want to think of it as 2 columns and 3 rows, but other times we might want to think about it, it might be helpful to think about it as 3 columns and 2 rows. And going from one to the other is called a transpose. So this is B, then this would be B transpose. So you can see it right there. So if you take the transpose of the transpose, you get back to the same matrix. And this gives us actually another way to write a dot product. So here's 2 vectors we're dotting. You can write it. This is a matrix product here, because we're going to take this row, this column, match it up with this row. I do the dot W1 times W2, etc. And this is written as a matrix multiplication. This is the dot product notation. And then over here, you can write it as a vector times a vector, a matrix times a matrix, but this one, you have to transpose it to get it to look like that before you can actually do the multiplication. If you get the same matrix, whether you transpose it or not, that's called a symmetric matrix. So here, notice like these are the same, these correspond to the same, these are the same. So you have a diagonal, and then those off-diagonal entries correspond to each other. They match up. We can talk about powers now, since we can talk about a matrix times a matrix. We can talk about a matrix times itself. So that as a squared, a matrix times itself 3 times. Notice it has to be square for the multiplication to work out. So powers of matrices only make sense if they're square. And a to the 0 we're going to define as the identity matrix. So again, that was 1. So you'd have 1s down the diagonal and 0s everywhere else. Okay. And there's an example of finding a to the 4th. They find a squared, then they multiply a squared together. So you guys can look at that more carefully if you need to. And that's it. So we'll see you in class. Still made it under 20 minutes.